You can look into that. And you should be able to read it because I've given you the basics. All right, so let's now look at a topic where we have an application of the complex Ginzburg-Lambda equation. So this is not a new topic. It sounds like it, but I will reduce the model that we study to the complex Ginzburg-Lambda equation. And what we will learn is a bit of population dynamics along the way. The most important technical aspect of this chapter is the so-called slow manifold reduction. So that means, as you will see, you have a higher dimensional space in which the dynamics takes place. And then you figure out, oh, it's not all the variables in this higher dimensional space that are actually important. I can reduce the dynamics to a few variables that are slow, and on that slow manifold, the interesting dynamics actually happens. Okay? And this will lead us to the complex Ginzburg-Lambda equation. So let me start. This is all in the field of population dynamics or game theory. And game theory and population dynamics have a very, very long history. Here I'll give you the history of game theory, which you can also read in a review article that I wrote some time ago. So it all starts with ideas from strategic games, so economics. John von Neumann and Oskar Morgenstern, they have been thinking about game theory in the terms of strategic games and equilibria. You may know Nash equilibrium as a basic concept of game theory, and his definition is an equilibrium in a game is reached as soon as no party can increase its profit by unilaterally deciding differently. That's a perspective of an economic situation. It's also a perspective which might not be correct in the nowadays, because it assumes that people are rational, and it seems that people become increasingly irrational nowadays in interactions. The later analysis of game theory was done by people like, especially John Maynard Smith and George Price. And they were thinking about games not in the context of a given situation where you have people interacting with each other that have a fixed strategy, but they were thinking of an evolutionary setting where you have many different species of different kinds, of different strategies, equal species, and they can change their mind along the way. Okay, they can be convinced by others, they mutate, they're selected. So you have a population dynamics, and then you want to know what happens in an evolutionary game in the long run, what's the steady state. And that's much closer in spirit to what we do here in physics, because in physics we study many-body interacting systems, and we want to know what's the outcome in the long run for an interacting many-body system. Okay? Now, here is a bit of a context that motivated the study I did some time ago. So the context is the following. You have E. coli bacteria, and these E. coli bacteria, they can exist in different forms, different strains. Here they're called collicin-producing, sensitive, and resistant strain. So what does that mean? It means that this strain, called C, is producing a toxin. This toxin is killing another bacteria, also an E. coli, that's sensitive to the toxin. So that means by lysis, so by killing it, the C strain is dominating over the S strain. Now the S strain is sensitive to the toxin, but it doesn't have the load to actually carry a gene in order to defend itself against the toxin-producing bacterium. So it has less effort to make for producing something, and it can invest that energy left over in metaphoric terms to grow faster. So as compared to a strain, R that would be resistant to the collicin that's produced by the strain C, it's growing faster than that. So it's dominating over the R strain, so S is dominating R, it outgrows R. And R, the resistant strain, is dominating over C because it also has a lower load in terms of metabolic cost since it doesn't have to make the toxin, so it's outgrowing C. And that's what you observe in experiments, and people have done these kind of experiments. What they've also found, and this is an experiment by Benjamin Kerr in the group of Bohannon in 2002, is that if you put these different strains, R, S, and C, on a Petri dish, then you start forming domains of C strains, of S strains, and R strains. And these domains, as you watch them over time, they grow, but they don't completely invade each other, so they live a happy coexistent life in the end, where you have a kind of biodiversity between the three strains. And what we wanted to know at the time is, how can we conceptually explain such an evolutionary outcome in a game where you have cyclic dominance? You can also call this a rock, paper, scissors game, because this is the same kind of non-transitive behavior as rock, paper, and scissors. You all know this game, and it's cyclic, right? Rock is damaging scissors, scissors is cutting paper, and paper is wrapping rock. So you have the same kind of cyclic dynamics. So what we did some time ago is to construct a model which is following the ideas of May and Leonard. They invented the model to begin with in a well-mixed scenario. So the model is conceptual. It's not identical to the experimental data that you saw, but it follows the same kind of spirit. You say there is one kind of competition in the system where you kill your neighbor. So A meets a B. So for example, the collysin producing strain meets a sensitive strain, and by meeting it, it's killing B and creates an empty site 0. That's called a contest competition. And now, to make things simple, make this the same in a cyclic manner for the interaction of B with C and of C with A. So they cyclically dominate each other and create an empty site by that. Now, once you have empty sites, these bacteria also reproduce. And you can have now, with a certain rate mu, A finding an empty site and reproducing itself. Same with B, same with C. So there's two types of competition in the system. One is called contest competition, and the other one scramble competition. Contest is interaction between different strains, and scramble just means you are fighting for resources and you try to occupy the empty space. That's a system that doesn't have any kind of mixing in there because things would just stay in space. Or you can think of this also as a well-mixed kind of system where these interactions you can think of happening in a container where things mix fast. So what we did in addition is to add a mobility in a way that can vary, but we did it in a way that we said, well, the species B and C or A and B or whatever you have on two different sites, they can interchange. So A can hop to a place where C is, and C can then, as a response, hop to a place where the A was. And that's happening with a rate epsilon, and these kind of interchanges between different sites leads, as you know, to diffusive behavior. So when you combine all of that, you get a diffusion reaction dynamics where the reactions are given by what you have here on the board, and the diffusion is then some kind of term that's Laplacian of the concentrations A, B, C. So let me show you what you get by putting this on a computer and doing the simulations. This here shows the patterns that you get as a function of the diffusion constant or the swapping between the different species given a fixed system size. And what you should notice is that the wavelength of the patterns that you see is increasing as you increase the corresponding diffusion constant. Meaning if you mix harder and harder, you create in the long run a situation where the system is completely mixing, and then you would get red, yellow, or blue as the outcome in the long run. It's only for small diffusion coefficients or large system sizes that you have these kind of patterns. The patterns you get are spirals, and when you look at movies, this is how they look like. These are spiral waves that run through the system, and they depend on the system size. They become these larger spiral waves when you have a correspondingly larger diffusion coefficient. And that's very reminiscent of a Ginzburg-Lambda equation, because that's one of the solutions you can get for a complex Ginzburg-Lambda equation. It's a oscillatory instability type of thing. It oscillates, here it spirals, and it has some kind of group velocity, which is the velocity of the wave in the spiral. So let's now start with that and develop a theory for that kind of system. Good, let's start. So we look at the May-Leonard model, and we want to see whether, and if yes, how, this can be written as a complex Ginzburg-Lambda equation. Before we go there, we need the corresponding equations for all our different species. So we will denote the concentration of A by A of x and t, and the same for B and C. And we will also introduce a total density rho of x and t, that's the sum of all the different species. That means if I now mean by A, B, and C the volume fraction of the different particles, that 1 minus rho is the density of the empty sites. So the first equations that we want to write down are what's called rate equations. And there I'm focusing on a situation where diffusion is very, very fast, so my system is well mixed. Then I can ignore the x dependence, so I can only talk about A of t, B of t, and C of t. I need to write down equations for A of t, B and t, and also C. So what's this equation like? Let us maybe go back to our scheme. Okay, so here we do have the corresponding scheme for the two types of competition. Right, so we can immediately write down the equations for that. So let's start from A and not write the A of t. So when does the A win? It wins if you look at this graph here, if it's encountering a neighboring empty site, and then it grows with a rate mu. And that means this is proportional to the probability of A encountering a neighboring site that's empty. So that's A times 1 minus rho. And then I multiply by the rate mu that creates an additional A. That is the scramble competition. I will lose. So again, we look here. When does the A lose? Well, if you look here, this is the case where it actually is losing. A is encountering a C. The C is killing the A. So this is then minus sigma times C. And the equations for B and C are the same as this equation. You have to just cyclically permutate the variable. So here plus cyclic permutations, giving the equations for B and C. That means in total, the equation for our vector of species will have the form of some vector field F as a function of A. So it is a 3-component ODE, which you can characterize in a corresponding phase space where you plot A, B, and C. What you want to know is the question that you're facing is, what is the geometry of the phase space? That's the key question. What this entails is that you want to know what are the fixed points and what are the corresponding manifolds that are invariant. Fixed point is easy, right? Fixed point just says if I plug in a fixed point, you should get 0 on the right-hand side. An invariant manifold is something more interesting. That would mean if you are on a submanifold in the 3-dimensional space, the dynamics will make you remain on that manifold. You don't get out of this anymore. That's an invariant manifold. So what about fixed points? Can you guess some?
The origin?
Yep. That's one. That's a trivial one. All are dead. That's for sure one.
Equal population of?
Yeah, equal population. So 1, 1, 1 with some prefactor. That's a very interesting one. Okay, so we have 2. If you have all A's, no B's, no C's, nothing will happen. So it's a fixed point. If you have all B's, again, that's a fixed point. Right? So the corners they are fixed point. This is here 1, 1, 1. And they are absorbing fixed points. Because there's no way of getting out. You get in, but once you're in there, there's no process that you can see here that will generate an A, a B, or C. For that, I would need some kind of mutation. Then I could get this, right? If you have all A's and there's a mutation of A becoming a B, then you could kick in and have a dynamics that's away from these absorbing fixed points. Without a mutation, these are absorbing. And as said, there is also this fixed point here in the center that is a absorbing fixed point. But that's a bit different. This point, as you make a small perturbation, what happens? You move away. While here, these fixed points, as you will see, they have some kind of attractiveness to them. Okay. There is an invariant manifold, which I'm drawing like so. So it's connecting these three absorbing fixed points. That's called the reactive manifold. And in this reactive manifold, sorry for putting it here, but this is the fixed point that you were talking about, where there's equal amounts of each species, and that's a reactive fixed point. Finding the fixed points is, as I said, super easy. That's a very simple calculation. Finding the reactive manifold is not so easy, because that's not necessarily any kind of plane. It can be something that has an interesting curvature and higher order effects to it. That's non-trivial to find. What I didn't talk about yet is what about stability of these fixed points. And I do the formal analysis in a second. So what you will find is that this fixed point is unstable, and it moves in this manifold, in this reactive manifold, moves and moves and moves, and as time goes to infinity, it will end up at closer and closer to the boundary of this reactive manifold, and comes closer and closer to the three absorbing fixed points. It never reaches them, in the same way as a radioactive decay never reaches zero. If you think about radioactive decay as a continuous real variable decaying to zero, of course, if you think about finite population size and stochastic effects, when you come closer and closer to the boundary, these stochastic effects become very, very important. And in the end, the system will pick one of the three states to then settle down. Okay, so that's the dynamics. And here's the summary. We do have this set of diffusion reaction equations. There's no diffusion yet. And these reaction equations have a phase portrait in 3 dimensions that's characterized by some landmark spaces, fixed points, and invariant manifolds. And to spoil my story, this reactive manifold is the important manifold in the whole system. Right? As you see from the flow, anything that's away from the reactive manifold is crunching down on it. So it's converging towards the slow manifold, and all the action then goes on in this manifold as it spirals out. Good, now let's do the math of that. So you see how this works out in detail. So fixed points. Well, we wrote them down: 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. They are the trivial ones. and a non-trivial one, which we easily guessed, right? Because we have a symmetric game, so it should be proportional to 1, 1, 1, equal amounts. There's a prefactor, and when you do the algebra, the prefactor is this ratio between the rate of mu and the rate of sigma. The next thing we want to do is a linear stability analysis. So let's do this as well. For that, you say that you have a deviation from A. So you have delta A equals A vector minus A star. And then you write down the equation of motion for, so let me call this here x. That's my deviation. And then I have dtx is equal the function f of A star plus this small deviation. And when I do Taylor expansion, this is f of A star plus the Jacobian of f evaluated at A star plus the rest, which is a nonlinear function of the deviation, and this has to be scalar product with x. So I want to do a little more than what we did previously. So previously I wouldn't even write down g of x because I only wanted to know the linear behavior and its stability. My goal in the long run is now to actually figure out what happens on this slow manifold. So for that, I do need to know what the nonlinear terms are because I want to characterize not just the tangent plane to the fixed point, but the actual form of the manifold close to it. So right when you look back, so what we want to know when we analyze the dynamics now is I'm here at this fixed point or any other one. Let's say I'm here. The Jacobian is the tangent plane. And I want to know the curvature of this. And that's encoded in g of x. Yeah, please go ahead.
So when we move away from the one that we will discover to be the unstable fixed point.
Yeah.
How you said that if we continue the expansion, we will find the geometry of the reactive manifold, but we are assuming that we will stay on the reactive manifold. But why is that? Is it because the fixed?
So that the reactive manifold is an object that exists in these systems, right?
We are assuming this.
Well, there's a theorem in theory of nonlinear dynamics that these things exist. And here we have an example of it. And I wouldn't worry about existence. There's a proof for that. So here you find that you have such a invariant manifold. And what we want to do is actually to calculate what it is. How does it look like? And the features on that manifold are important for us. Right? If you do a linear stability analysis, I only will learn about linear behavior, so I will not be able to get something like a complex Ginzburg-Lambda equation. No way, because there are nonlinear terms in that equation, and I wouldn't have them. So what I'm trying is I'm trying to project in the long run on that yellow manifold and find a way of rewriting my dynamics on that manifold in a particularly simple form.
And the possibility of this is strictly, closely related to the symmetry that we have between the A, B, and C, right?
So things are simple because I took it symmetric, and the algebra is still messy, but easier. You can do the same analysis, much more complicated, of course, if you don't assume the symmetry in the coefficients of the rates for scramble and contest competition. Yeah. All right. Other questions? All right. So this here, right, this is 0 because we have a fixed point. And that means the equation that we have is the Jacobian x, and this here is my Jacobian times x plus g of x. So let me sketch just what we are aiming at. The first thing is we focus on the linear part. So just on J. If we do that, we will find eigenvalues and eigenvectors. The eigenvectors, right, they will determine the tangent plane and also the, not necessarily, but here it is, orthogonal direction to it. And the eigenvalues, they will talk about the stability of these, in these directions of the eigenvectors. Again, going back to my picture here, one eigendirection will turn out to be this arrow here that I call YC. So pointing out, perpendicular to this reactive manifold, that's a stable direction. We'll find this. All the flow will go towards the manifold. And on the manifold, there's two eigenvectors in this and that direction, and they correspond to an oscillatory instability. So that's one thing we want to do. The second is, so we transform into the eigenspace that we found by this analysis. That gives rise to what's called a Jordan normal form. Simply not a diagonal matrix, but something that has also off-diagonal elements, because this is not a Hermitian matrix, so we have complex conjugate pairs of eigenvalues. And then, in the third step, we simplify the equations in the eigenspace also accounting for the curvature of the reactive manifold. Okay. The third step is something which will become clearer to you as we go along. So it's not just transformation to the eigenspace. In the eigenspace, we then look at the curvature of the reactive manifold and then try to make transformations which are actually nonlinear transformations. They will then help us to simplify dynamics and then reach something that's called the normal form of the dynamics, which is not the same as the Jordan normal form. That refers to linear stability analysis. Normal form then would mean the simplest form we can write the dynamics once we have projected on the slow manifold. Great, let's continue then. First step of the analysis is the linear stability analysis and also calculation of the remaining nonlinear term. And this is algebra, which is actually pretty trivial. If you want to look at it, it's my lecture notes, but I'm sure you can do this by yourself. Calculating the Jacobian gives you this structure, mu over 3 mu plus sigma, and then mu plus sigma. You can guess the second line. Yeah. It must be cyclic. So you cycle just the first line. So mu plus sigma, mu plus sigma, mu. And that's a beautiful 3 by 3 matrix because it's a circulant matrix. And there is nice theorems of how to calculate the eigenvalues and the eigenvectors just in one go. I'll show you. So they are very nice in terms of mathematical properties. We can also calculate the g of x. And that's just for your reference. You'll need it if you do later the calculation of the invariant manifold. The structure is like so. So it's mu xa squared, and here's a minus, minus mu xa xb minus mu plus sigma xa xc. Right, and you can guess the other two lines. I won't write them down because they're again obtained by cyclic permutation. And you should notice this is not that difficult, right? The linear part and the nonlinear part is quadratic only, as it must be because our starting equation, this one, had only quadratic terms as the nonlinear terms. So what about the eigenvalues and the eigenvectors? I already told you it's a circulant matrix. So hope I did the sign right. No, there's a minus here. I forgot that. And let me call this here then A. So A has the structure that in the first line you have here C naught, C1, and C2. Right? This is the first line. And that's all that matters because we have a circulant matrix. And once you know this first line, we can write the eigenvalues and the eigenvectors. So the eigenvalues, lambda k, they are given by C naught plus C1 omega k plus C2 omega k squared. So it's just a linear combination of the first row, C naught to C2. And the omega k's are phase factors. So the e to the 2 pi I times k over 3, k equals to 0, 1, and 2. The eigenvectors that correspond to these eigenvalues, psi k, they are 1, omega k, and omega k squared transpose. So see, it's really very simple structure. If we want to know the eigenvalues for my original matrix, of course, this is then minus mu over 3 mu plus sigma times the eigenvalues of the matrix A. The eigenvectors are, of course, the same. So what kind of eigenvalues do we get? Well, there's one where k is equal to 0. Right? For k equal to 0, you just add C1, C0, C1, and C2. So k equal to 0. In that case, you get lambda naught equals to minus mu, and psi naught equals to 1, 1, 1 transpose. And the eigenvector you could have guessed, because that's pointing to the reactive eigenvalue which has equal composition of A, B, and C. And that's the one direction which is a stable direction. So along that direction here, this one, the flow goes towards the reactive fixed point. There's a negative eigenvalue. For k equal 1 and 2, if you insert what we have here, you get a pair of complex conjugate eigenvalues. So for that, you get lambda plus minus equals C1 plus minus I omega. Okay, I'm now a bit silly in my notation. Let me call this different here. Hope I don't mess it up later. D1 plus I omega with D1 equals to a half mu sigma over 3 mu plus sigma, and the omega being square root 3 over 2 mu sigma over 3 mu plus sigma. And the eigenvectors, psi plus minus, they are equal to, let me do them differently. Psi plus is 1 omega squared t, and psi minus is 1 comma omega squared omega transpose. All right, so we found explicitly what I told you in words earlier. This direction is stable, and then in the vicinity of this reactive fixed point, which is actually unstable, right? D1 is positive, so it moves away, but it has a imaginary part, so it spirals away from the reactive fixed point. One stable direction and one where you have an unstable spiral. This is a stable direction and this is a unstable spiral. So next what we do is we transform into the space of the eigenvectors. That we do by a variable transformation. We now want to go to the variables y by a transformation matrix S. Right? So we rotate from the axis CAB to the axis YC, YA, and YB. And correspondingly, you have the inverse transform. So X is S to the minus 1 Y. And let us write down this matrix S. This is some prefactor, which we are free to choose because we can just normalize things properly. Now, these are the eigenvectors of our problem. And one eigenvector is the trivial one, 1, 1, 1. Right? So here 1, 1, 1. That's one vector in our transformation matrix. And we normalize it, so it's 1 over 3. And then we need to have the two other directions that we want to transform into. And there it doesn't matter what we choose. It doesn't matter only in the sense that they need to be orthogonal to this one. That's all we need to worry about. Otherwise, you have a nice rotational symmetry in this YB, YC plane because of the cyclic symmetry of the problem. And that's why we can choose it so, like so, 1 to minus 1, right? So if you make the math, this is orthogonal. And then square root 3, 0, minus square root 3. You do the math, it works out, right? These are orthogonal, and those are orthogonal. They're all normalized. All right, so that's how you transform. And then you do have the corresponding form of equations in the transformed variables. So for that, you then get dt y is j y plus h of y. Calculating the h of y is not difficult, but a lot of algebra, as you can imagine. It's a lot of terms that enter there. And I will not write it down. The only thing I will give you is j tilde, because that's the Jordan normal form. Of our problem. It has to have a block diagonal form. In the lower part, we need to put the one corresponding to the stable direction. That's minus mu. Right? And here, that block is the second Jordan block that we have, corresponding to the spiral, the unstable spiral. And there we have d1, d1, which is positive, and omega minus omega. So again, what you see here, this is our stable direction, and that block is the unstable spiral. Yeah, don't do this. I don't write down the h of y because it's not very instructive. It's just some equation which is quadratic in ya and yb and yc. So h of y is quadratic in y. So the next really important step that we have is the fact that we look at a invariant manifold. This invariant manifold is this yellow object that you see here, and I want to calculate it. So a manifold like that one, so yc equals m of ya and yb. This is our reactive manifold. And it has a few properties. The first one is that manifold has to reduce to the tangent plane in the linear case. That's fine. Okay, so has to reduce to tangent plane in linear order. We want more. We want to go beyond linear order. And that just means at yc equal to 0, you have to have m equal to 0, because we're already at the tangent plane in the new coordinates ya, yb, and yc. The invariant manifold has to have another property, namely if you write it down and take the time derivative of it, this relation needs to be valid such that I remain on that manifold. So I just write this as the sequence of partial derivatives. Okay, so it's left invariant under the dynamics. That is what defines an invariant manifold. And that's what I'm using here. It's left invariant under the dynamics. All right, the rest is algebra again. And maybe you can kind of guess the structure before we, look at the result. So what did I tell you about ya and yb? It's a cyclic system, so it's rotational invariant locally. And that means what you expect is a parabola that spans out from the tangent plane. So you expect the yc be proportional to ya squared plus yb squared. And all you really have to determine by the algebra is the prefactor. The prefactor has to be such that this is an invariant manifold. Good, now let me show you what you get. This is the invariant manifold. So it is a parabola at this point, which is the reactive unstable fixed point. You see here it's quadratic in ya and yb, and there's a prefactor to it. So now we have it. Now we have the dynamics on that manifold. So when you look at the equations that we have now in total, it's this equation, which is in terms of YA, YB, and YC, right? Those are the three variables that define this equation. Now I'm knowing on the slow manifold what the relation between YC and YA and YB is. So what I'm doing is I'm eliminating this one in favor of YA and YB by inserting that expression that you have there in this relation here. Okay. Again, there is a few steps of algebra, and then you get an equation for YA and YB. So don't be scared. They have a very simple structure. So there's a linear part. The linear part is something which is just described by the linear equation. So that's not really the tricky part. And then there's this horrendous looking quadratic part that you have here. So it contains lots of terms here that are proportional to YA squared, YB squared, and then third order terms, etc. So a lot of different terms that you get, and I'm neglecting here terms which are small o in y to the 3. So something that appears here is higher order than y to the 3. I'm keeping everything here up to third order in y. And that's already the slow manifold equation. That's the equation you end up with. And now you say, this looks way too ugly for me. I want it simpler. And there's a method where you can do simplifications of nonlinear equations. That's called normal form reduction of nonlinear equations. That's a branch in mathematics, especially in applied math when you study nonlinear problems. And there's a standard procedure of how to do this, how to simplify such an equation to its very core. So to find a nonlinear transformation of variables to new coordinate C such that you get the simplest form you can write this in. And it's beautiful that something like that exists, right? You can find by linear algebra a transformation from Y to C such that you get the simplest form for this nonlinear equation. That's again a lot of algebra which I want to spare you. So this is a transformation to the normal form, and this transformation turns out to be this. So instead of the variables YA and YB in the eigenspace, you define a new set of variables ZA and ZB. If you know them, you're done, but you have to construct that. That's the tricky part. And once you have those variables, you can insert these variables right here and arrive at an equation for Z. Okay, and this equation for Z, I'll write down for you, because it's a key finding. So you do that transformation, and then you get the equation for ZA and ZB, and this is called the normal form of the dynamics on the slow manifold that we constructed. It reads like so. It does have and now I need to reintroduce my symbols C1 and C2 and C3, because they are then part of my Ginzburg-Lambda equation. They're not the C's that I defined there. What you get is a core that is not surprising. Okay, and this is actually my D1. So sorry for that, but I want to call this C1 because I need it in the Ginzburg-Lambda equation. That's not surprising. That's the core which has this complex conjugate pair of eigenvalues. Right? This is the outward spiral. The non-trivial part is the nonlinear term. And this nonlinear term has the structure CA plus C3 CB CA squared plus CB squared plus order C to the fourth, higher order terms. And this has a structure that by symmetry looks like so. And the omegas and D1 are already defined, right? The omegas are, where are they? They're somewhere. So let me write them down again. Omega 1 is square root 3 over 2 mu sigma over 3 mu plus sigma my C1, which used to be a D1, is a half mu sigma over 3 mu plus sigma. That's C1. C2 is sigma 3 mu plus sigma 48 mu plus 11 sigma over 56 mu. So just some linear combination of all these things. And C3 is square root of 3, 18 mu plus 5 sigma okay. So all some kind of functions of mu and sigma that come from the algebra of the problem. And that's our normal form, the simplest way I can write the dynamics. And you can make it even simpler by defining a complex amplitude. And once you do that, then the equation has a form which we talked about already. That's exactly the Stewart-Lambda oscillator form that we had previously. Okay. That is the reduction scheme that we had. So sorry for going a bit over time, but let me summarize. So we wanted a reduction of the May-Leonard dynamics that has 3 variables. And what we arrived at is the complex Ginzburg-Lambda or Stewart-Lambda oscillator form. There's no diffusion yet. And the way we did this is a very standard scheme that you can repeat as you have it for all other systems that you encounter. You first make a linear stability analysis and transform to a system that are the eigenspace of the linear problem. This is the eigenspace problem with J the Jordan normal form and Y in the direction of the eigenvectors and H the nonlinear part of dynamics. Then, in this case, and maybe in other cases as well, there is a reactive manifold on which you have a stable, unstable fixed point where everything condenses in terms of its dynamics, and you eliminate YC and write an equation in terms of YA and YB alone. And that has a structure which has the linear core from the linear stability analysis, so the outward spiral, plus some nonlinear stuff, which you can write as functions of y and y squared and y to the third. And the final step is the most beautiful one I find, is you find a nonlinear transformation that rewrites this form in the simplest form you can imagine. As said, this is a linear algebra problem in the end to find a nonlinear transformation. And then once you have found this nonlinear transformation, you do get the normal form, which is this, which is the Stewart-Landau oscillator. All right, that concludes it for today. Next time we then study what happens as you add space. So what kind of phenomena you get when you look at the diffusion equation of the complex Ginzburg-Lambda type. Thanks for your attention.